You have a heated plate that can be represented by this PDE, where the U is the temperature, X and Y are the coordinates where you measure the temperature. So you can assume this direction is X and this direction is Y axis. When we see this heated plate at the top view, you should be able to look the item in this way. There are several boundary conditions and initial conditions here. The dimension of the plate is given by A and B, which means the X length here is equal to A and the Y length here is equal to B. The heated plate is insulated in this region at the X equal to 0 and this region at X equal to A. Therefore, the heat flux to pass through the heated plate in this direction will be equal to 0, since it has been insulated, similar to this region. And we know the heat flux is proportional to the temperature gradient. So in this case, is the temperature gradient in the X direction. Therefore, the temperature gradient with respect to X-axis will be equal to 0 when the X is equal to 0 here, and also at X equal to A. In this example, we are using the U as the temperature, therefore we should change this symbol to du, and you should obtain these two boundary conditions. The temperature here is maintained constantly at temperature equal to 0, and this location is at y equal to 0 for multiple x. Therefore, you can write your temperature at various x locations at y equal to 0 will be equal to 0. So this is the boundary condition here. The boundary condition here is given by u equal to fx. This means that the temperature distribution here is depend on the x dimension. For example, if you have the fx equal to 5, then the temperature will be constant here, which is equal to 5. If you have the temperature equal to 5 plus x, that means the temperature will increase in a linear pattern over the x dimension here. So if you have additional x squared term here, it means the temperature will increase in a quadratic manner with respect to x dimension here. So bear in your mind, the temperature equal to fx here means the temperature here might not be constant over the x dimension. This boundary condition here is at y equal to b. Therefore, the temperature at y equal to b for various x location here is equal to fx. So this is the second boundary condition here. So you should know the dimension for the x is from 0 to a here, and the dimension for the y is from 0 to b here. And you can also write this into ux, which is the first derivative of u with respect to x, and your x location is at a for various y location, and your y is from 0 to b. So this one you can also write it to ux. So your x is 0, and you have multiple y locations, which is equal to 0. So these are the 4 boundary conditions for this PDE, and you are going to use that to solve the temperature at various x and y locations. Previously, we have tried to use the b squared minus 4ac in order to identify the Laplace equation here equal to the elliptic PDE. To obtain the PDE solution, which is u with respect to x and y here, we can use the separation of variable method by having the solution equal to the multiplication of two functions for the independent variable here, which is capital X multiplied with capital Y. Capital X here indicates the x function, and capital Y here is the y function. Then you need to differentiate it according to the PD equation. Differentiate u with respect to x twice, then you obtain x double prime y. Differentiate u with respect to y twice, you should obtain xy double prime. Then you need to separate the variable on the left hand side and right hand side. So you move this to the right hand side, you obtain negative. And then you shift the x to the left hand side, shift the y to the right hand side. And you should obtain this equation. And we let this equal to negative lambda in order to obtain 2 ODE. So when you compare the first component here with the third component, you obtain the first ODE. Compare the second component with the third component, you obtain the second ODE. For this first case, you assume the lambda equal to 0, substitute inside these 2 ODE, you should obtain the new ODE to be this. And you need to solve these 2 ODE by using the characteristic equation approach. From here, you found the root to be double 0 or repeated 0. So if you substitute inside the solution here, then you obtain 2 dependent solutions for the y function and 2 dependent solutions for the x function here. To obtain independent solution, then you need to do the treatment by multiply the independent variable. So in this case, your independent variable is y, you multiply it with y. And in this case, you need to multiply x because x is the independent variable. Then you can multiply the constant c here with these 2 solutions and take the summation, and this is called the superposition principle. By doing this, you combine 2 solutions into the total solution. You repeat the same procedure here to obtain the total solution for x function. Then the exponential 0 is equal to 1. This gives you a simplified version for the x and y function here. You need to multiply the x and y function here, which gives you the PD solution for the first case, which is equal to this answer. For the second case, we assume the lambda equal to negative alpha square, substitute inside this to obtain the new ODE here. Now we are going to solve these 2 ODE. So you are using the similar approach. By performing the characteristic equation approach, you obtain the root. Since the root here is plus minus alpha I in imaginary number, therefore we can convert it into sine and cos format. Since the root here is equal to plus minus real number alpha, therefore you convert it to the hyperbolic cos and sine format. When you multiply the x and y function here, then you obtain the PD solution for the second case, which is equal to this. For the third case, we assume the lambda equal to alpha square, and you substitute inside these 2 ODE to obtain this, and you need to solve these 2 ODE. So you can use the characteristic equation approach, and you obtain the root plus minus real number in the first case, then you obtain the y function here equal to hyperbolic cos and sine. And you obtain the root equal to plus minus imaginary number, therefore you obtain the answer for the x function here in the cos and sine format. So take the multiplication between the xy function here, and you obtain the PDE solution for the third case, which is equal to this. This is the PDE solution that you obtained so far for the first case, second case, and third case. Solve the unknown coefficient for the C1 constant until the C12 here. You need to apply the boundary condition. We have 4 boundary conditions in this case. Normally we will use the boundary condition with a lot of zeros in order to simplify the problem. Let's apply these 2 boundary conditions first. Since the boundary condition requires to differentiate the u with respect to x here, therefore you need to differentiate the u for each cases here with respect to x. When you differentiate with respect to x, your y component here will be remain. And you differentiate the x component here, constant here will be cancelled, and your c4x will become c4. So this is the first solution. Differentiate hyperbolic cos and hyperbolic sine, you obtain hyperbolic sine and hyperbolic cos. And don't forget to multiply the coefficient inside. So So this is the solution for the second case. Lastly, differentiate cos give you negative sign, and differentiate sine give you cos. And don't forget to multiply the coefficient inside. So this is the solution. Let's apply the boundary condition for the first case here. So you need to substitute the x equal to 0 inside this equation, and you obtain the du over dx equal to 0. Since you don't have x here, so this is just remain. So the multiplication between these two functions will be equal to 0. So the first possibility is c1 plus c2y equal to 0. So if you draw a graph for c1 plus c2y, you obtain a linear graph. So you can see that the c1 plus c2y here can be only equal to 0 at one point, which is at y equal to negative c1 over c2. However, your c1 plus c2y here must be equal to 0 for the y in a range from 0 to b. It's not just one point. Therefore, in this case, the c1 plus c2y cannot be equal to 0. In simple, c1 plus c2y here equal to 0 is only valid at one point. But in this case, since our y is in a range, therefore this is not valid. Since the c1 plus c2y here is not equal to 0, therefore the c4 here must be equal to 0, so that the multiplication of these two components will be equal to 0 here. Since we know c4 is equal to 0, therefore we can substitute inside the PD solution here to obtain the new PD solution. So you can multiply the c3 inside in order to obtain the new constant a1 and b1. If you apply the second boundary condition, when x equal to a, the differentiation of u with respect to x will be equal to 0. Then you should obtain this, and you see that this equation is exactly the same with the first equation here. Therefore, you obtain the same result. With that, we success to obtain the solution for the first case, which is equal to this answer. We continue to apply the boundary condition for the second case. So you substitute x equal to 0 inside. Then you obtain the du over dx equal to 0. Hyperbolic sine give you 0. Hyperbolic cos 0 give you 1. Therefore, you should obtain this equation. So this component can be eliminated, and then hyperbolic cos 0 give you 1. Therefore, you only have alpha C8 here. So you continue to analyze which component will be equal to 0 to make it equal to 0 here. Assume that the C5 and C6 here is non-zero. Then if you take the computation of this with the y is changed from 0 to b, then most of the time you obtain this is not equal to 0. Therefore, this component must be equal to 0. Since alpha is not equal to 0, because the alpha is greater than 0, therefore your C8 must be equal to 0. So you success to obtain C8 equal to 0, you can substitute inside here to obtain the new derivative, which is equal to this. Let's continue to apply the second boundary condition. When your x equal to a, the derivative will be equal to 0. So this will be equal to 0 when you substitute x equal to a. So you should obtain this equation, and we know that the cos and sine term here cannot be equal to 0. Therefore, this term must be equal to 0. And the alpha here cannot be equal to 0 because alpha is greater than 0. Hyperbolic sine alpha a here is not equal to 0 as well, because the alpha is greater than 0. A is the length for the x-axis here, so when you multiply alpha with a, it will be still greater than 0. And we know that hyperbolic sine for a positive number, it will be always greater than 0. It's not equal to 0. So your C7 here must be equal to 0 to make the whole multiplication here equal to 0. In this case, you success to obtain the C7 and C8 equal to 0. Therefore, if you substitute inside the PD solution here, 0 multiplied with this, you obtain the U2 equal to 0. Therefore, there is no solution in this case. We continue to apply the boundary condition for the third case. When your x equal to 0, the derivative will be equal to 0. So this will be equal to 0 when your x here is equal to 0. Cos 0 give you 1, and sin 0, this term will be cancelled. So you should be able to obtain this equation, and the hyperbolic cos and hyperbolic sin here cannot be equal to 0 for your y from 0 to b. Alpha here is greater than 0, therefore this is not equal to 0 as well. So your C12 here must be equal to 0 to make the multiplication here to become 0. So you can substitute C12 equal to 0 inside here. So you obtain the new derivative to be this. Let's substitute the second boundary condition. Substitute the x equal to a inside. Then you obtain the derivative equal to 0. So from here you can see the hyperbolic cos and hyperbolic sin here cannot be equal to 0. And the alpha here cannot be equal to 0. Sin alpha a here will be equal to 0 when the alpha a is equal to n pi, where the n is equal to 1, 2, 3 and so on. Consider the alpha is greater than 0. Since the sin term here can be equal to 0, therefore the constant here can be equal to non-zero. If the C11 here is non-zero, then you have the solution for the PDE in this case. So after you apply the second boundary condition, you obtain the hyperbolic cos and hyperbolic sin here not equal to 0. And you know that the constant here is not equal to 0 when the sin term here is equal to 0. For the alpha a equal to n pi, and if you rearrange, you obtain the alpha equal to n pi divided by a. And you should know the n index is starting from 1, 2, 3 and so on, because the alpha here is greater than 0 in this case. So you can substitute the alpha inside this equation, and you should obtain this, and multiply the constant C11 with the constant inside. You should obtain the constant A3, B3 here. Since you have n index from 1, 2, 3 and so on, therefore the U3 is changed from single solution into multiple n index solution. So this is the solution for case 3. Don't forget the n here to indicate multiple solution due to the n index. This is the solution that you obtained so far for 3 cases. For the first case, lambda is the eigenvalue, and in this case the lambda is equal to 0. And the solution to the PDE here is called the eigenfunction. So for the second case, U2 equal to 0, therefore there is no solution, no eigenvalue and no eigenfunction in this case. For the third case, your eigenvalue is equal to alpha square, where you know the alpha is equal to n pi divided by a. So substitute inside, you obtain your eigenvalue equal to this answer, and the eigenfunction is just the solution here. For example, you can substitute n equal to 4 to find the eigenfunction at mode 4, and this is the corresponding eigenvalue and eigenfunction. So eigenfunction here is the solution to this PDE. So if you substitute this inside the equation here, you should obtain left hand side equal to right hand side, which proves that this is the solution to the PDE. So you need to combine the solution from case 1, case 2 and case 3 to obtain the total solution. So this is called the superposition principle. Since the case 2 is equal to 0, then you just take the summation of first solution and the second solution from case 3. And you need to be careful, this is the multiple solution with n index. So when you take the summation of all of the n index solution, then you obtain the summation term here. From n equal to 1 to infinity, you can further simplify this series by multiplying the cos term here inside. Then you're able to obtain these two components. So you have 4 unknowns in this case, a1, b1, a3 and b3 here. So let's continue to apply the third boundary condition to find this coefficient. Substitute the y equal to 0, then your u will be equal to 0. So you substitute y0 inside. Hyperbolic sine give you 0, so this term can be cancelled. Hyperbolic cos 0 give you 1. Therefore, this term will remain a3. So b1y here cancel, so you only have a1. So you should be able to obtain this equation. So you should recognize this to be a constant plus a summation of cosine term here is a half-range Fourier cosine series expansion. Once you recognize this is a format for the half-range Fourier cosine series expansion, then you can obtain the coefficient a0, an here by using these two formulas. In this case, you should recognize on your right hand side here, 0 is your fx. So substitute fx equal to 0 inside. You integrate 0, you obtain 0. So this one also the same, you integrate the 0, you obtain 0 as well. So in this case, we obtain the coefficient a1 and a3n here. After you compute using these two formulas, you obtain 0. So a1 is equal to 0, substitute inside the original PDE. a3 is equal to 0, you substitute inside here, you cancel this component. There is a missing equal symbol here, please correct it. And after you substitute the a1 and a3, you should simplify the PDE solution to be this. There is a correction for the formula here. So since you have the fx function, so everything must be in x variable. So you should change all the t variable here into x. After you apply this PDE solution, you success to obtain this PDE solution. Let's continue to apply the last boundary condition here. Substitute the y equal to b, then you obtain your u equal to fx. So all the y here, you change to b. And in this case, your u will be equal to fx. Since you have a constant plus a summation of the cosine term, you should recognize this is an even function and it can be represented by the half-range Fourier cosine series expansion. Compared to the formula here, your a0 will be equal to b1b and your coefficient here will be equal to an. So n here remain and your omega is equal to pi divided by a. So omega equal to pi over a. Your fx function is the same here. Since you are integrate with respect to the x direction, therefore your x is from 0 to a here. So you can see your tau here is actually the maximum finite interval, which is equal to a here. For the half range expansion, you know that half period is equal to the tau and half period is equal to L symbol here. L and tau are equal to a here. Therefore, you can substitute all the L and tau here equal to a. And the omega is equal to pi over a. So by using this, you can solve the a0 and an. So you should be able to obtain the omega, L, and tau to be substituted inside this formula. Let's start to solve the a0. So in this case, your a0 is b1b. So substitute the a0 equal to b1b here, which is equal to this formula where you substitute the L and tau equal to a here. So after you substitute L and tau equal to a, you should obtain this formula. And you can shift the b to the right hand side, and this is the solution for your b1. Normally the fx function here, as well as the a and b coefficient here, will be provided. For example, the fx function here is given x, a here is given 2, b here is given 3, let's say. So you can continue to substitute the fx equal to x inside, a is equal to 2, and b is equal to 3. 3 multiplied 2 here give you 6. So after you solve this, you should obtain a constant for the b1. Since fx, a, b are not given in this case, then we just remain in this answer. So you have success to obtain the b1 coefficient here by using the a0 formula. Let's continue to obtain the coefficient here by using the an formula. By you compare the cost component here, then you can find your omega is equal to pi over a. So you know that omega is equal to 2 pi divided by t, which is the period, or is equal to pi divided by the half period. So in this case, when you compare it with the first equation here, your half period L will be equal to A. And you know that L is equal to P divided by 2. And for the half range expansion, P divided by 2 is equal to the tau. So you obtain the tau and L equal to A. So you can substitute inside. And your omega here is equal to pi divided by A. So you see you obtain the same omega, tau and L like the previous case. And you can use many approaches to obtain it. So your AN here is the coefficient for the cos term, which is equal to this. So you put this in the left hand side, and this is equal to this formula, where you substitute the L tau equal to A here, and the omega equal to pi over A. So after you substitute inside, you should obtain this, and to obtain the B3 coefficient, you need to shift the hyperbolic sign here to the right hand side. So this is the answer for the B3 coefficient. So far you have success to obtain the B1 and B3 coefficient for the PD solution here. So after you substitute inside, then you should be able to obtain the particular PD solution for this problem. In this example, you have the same PD problem and boundary conditions similar to the example 1. The fx function is provided in this example, which is equal to 100 degrees Celsius. It means at this boundary condition, the temperature will be always maintained at 100 degrees Celsius. And also the length for the x dimension and y dimension are provided, so your A and B coefficient will be equal to 1, where the length here is 1 and the length for the y-axis is 1 as well. Since you have the same problem with the example 1, then you can use the solution obtained from the example 1, where the coefficient B3 and B1 here is equal to these two equations. So you can substitute the A and B here to be 1, and fx is equal to 100. Solve this, and you obtain the B1 equal to 100. So you can substitute the B1 equal to 100 in the PD solution here. You continue to solve the B3 coefficient. So substitute the A, B by 1, as well as the fx equal to 100. So after you substitute the information, you should obtain this equation. Integrate cos, give you sine, and don't forget to divide with the coefficient inside here. Substitute the x limit equal to 1 inside and x limit equal to 0 inside. You should obtain this. So you can substitute the B coefficient inside the PD solution here, and you should be able to obtain this final answer. This formula can help you to compute the temperature distribution on the heater plate at any point here. So for example, if you want to know at x equal to 0.5 and y equal to 0.5, which is the center of this plate, and you need to substitute the x and y here equal to 0.5 by computing this series, and you can obtain the temperature at this point. This formula is only valid for the x between 0 and 1 and the y between 0 and 1. If you substitute the x equal to 1.5, which is outside the range for this is invalid because the original physical system here, the range is only within 1. So if you compute outside this boundary, then you are computing something not exist.